Morning everyone. This is lecture number 35, E524 Digital MOS LSI Circuits, and today November 13, 2020. So previously we were studying on various memories and its architectural level design, where it uses column decoder, row decoder and other circuitry, and along with that there are some cells which are SRAM, DRAM, and many other things. Like we also studied some part of read-only memory also, right? And we also just touched about floating gate transistor as well. Not the complete operation, but its symbol and how it's useful in the design of non-volatile flash memory. Okay, so later on again we are going to touch this, but not today. I just give its architecture. In the architecture we have studied SRAM, and in SRAM we have also studied 60 cell, 80 cell, 12T cell, which are actually the dual port. And we also studied the DRAM, where DRAM was storing the data on a capacitor, and the ratio between these two capacitors with respect to VDD by 2, you can have the stored data is logic or 0. So it depends. Delta V is going up or down. So if delta V is going up, then through the sense amplifier you can have the digital logic 1, and if it is less than like it's in minus, then the digital logic will be 0. So as we were talking about different kinds of ROM and also the floating gate transistor previously, we can proceed further with the different design. Like there is something called serial memories. This is again a repetition of what you have studied in the digital electronics, where shift registers were used. You can see the first one is having, like, first of all these boxes are D flip-flops, right? And it's a plain D flip-flops, and each one of the line are 8 bits, and this is designed for 32, designed with 32 flip-flops, where each one of the flip-flop is actually the 4 bits. So for a like bus of 8, you will have 32 flip-flops requirement. But this requires lots of flip-flops if you are going for more and more number of bits. So in that case, you can again use dual ported SRAM. Dual ported SRAM is 8T or maybe 12T SRAM, where you have read and write lines separately, which is not going through the reading of bit and bit bar. So that we can do with the specified clock, and with respect to clock you have the counting going from 000 to going at the higher side, and again the counter which is going from all 1 to higher side. So one of them is acting as a read address and one of them is acting as a write address for port SRAM cell. So that is what you can do over here to design a shift register. So each clock is going to give you the delay, right? So the D out is available after few number of clock cycle. It's like a pipeline, and once the data is available, it's with the latency of as many number of stages, you can have the output in the first one. But here this is the continuous one, and it's depending on what clock value you are giving, and with respect to counting thing, you can have the output. So it's output streaming is happening, which is happening with respect to D out. However, there is another way where, like, there are multiple ways. These are the 3 ways given in the book, like West and Harris. However, there are many ways to design such shift registers, where this is like a mux. So if one of the input is 0, the output is actually the selection will be depending on the selection line, and it's depending on the when there is a reset and when there is a availability of the clock. Accordingly, the output will be given, and different words can be read and write accordingly. So this is very simple thing which is already been taught earlier in your other course. Other thing is, okay, there is one spelling mistake. It's tapped delay line where different delays are there, where each of the shift register are incrementing by 2, and everywhere like these are the implementation with the flip-flop, and you are fixing the availability of the output with respect to the different delays. So this is also similar to what we have studied in digital electronics. So I'm not going into much in detail because we can spend time on the real thing. So one more is you can either having serial in and parallel out, right? Or you can also take parallel in, serial out, right? So each of these structure has this box, which is actually a flip-flop, and all these are positive age triggered flip-flops, and of course these designs are the synchronous one. If you want, you can go further and you can have asynchronous design also to have serial and parallel memories, right? For the completeness, there is one more thing which is called Q. Q memory has FIFO and LIFO, means first in, first out, where you might have various things as an input like write clock, write data, read clock, read data. These are the handshaking signals which are used in most of the microprocessors and the computer organization things. So in that case, to uh, to have the proper things, there is something called flags are available. So if this Q flag has full, means there is nothing can be written extra, or but it can be read. If it is empty, so you can write the data but could not read the data accordingly. You can have those things. So first in, first out is the one where it's a queue. So like a shift register, it's a first first in, first out is organized as a circular buffer, and whenever you are going to reset it, it's going to be empty, and whenever there is a like read pointer uh, will be there, you need to have the FIFO as a full. If FIFO is full, then and then you can read the data because the data is available. And other side, when it's empty is equal to 1, means you can write the data. And every writing the data requires resetting the whole queue, and then you can accordingly you can write the data whichever you want, and it depending on what how many number of beats are there. And inside queue you can have the same detail which you have designed for the case of the previous serial memories. So here you can again make serial memory or the serial register which is acting as a FIFO. And if you want to have not like first in first out, but you might be interested in last in and first out, so that is actually the stack entries. And stack entries are useful in the microcontrollers where stack subroutines are there or interrupt stacks are there, where such kind of things are there. And in that case, you need to accordingly design a circuit, or you can say that it's a kind of an FSM, finite state machine, which is going to be useful to make such a circuit, right? So these these things were already there, but now the most important topic, like after studying SRAM, where it was like this, right? This was bit and this was big bar, this was word, and you can like read and write the data accordingly. And in the case of DRAM, it's a dynamic data where you can read the data on a capacitor, and of course it's a ratio of C bit to C cell, right? And whenever you are starting with, it's pre-charged to VDD by, whenever you are starting with these two lines in SRAM is pre-charged to VDD, right? Through the pseudo NMOS structure, right? In this case also you can use the pseudo NMOS structure with the pre-charge to VDD by 2. So these two are very important when you are designing, and most of the people are designing as a project. But the most important part Like I could have introduced that one also as one of the project. I thought maybe I could not cover it on time, so I haven't kept it. But those who are interested, they can also design if they want to design TCAM. So it's called ternary, or before going to let's say ternary, it's content accessible memory. This is the most important memory in terms of checking the having two things like virtual address and one is the physical address, which is part of any microcontroller. So it matches these two things like virtual and physical address. If they are matching, it gives that match equal to 1, or you can say that this is the specified key which is actually compared, right? So if match is equal to 1, it's matching. If it is 0, it's not matching. If it is not matching, you can say that like there is something, some more bits are there like miss bit. So if it is not matching means mismatch, you can have miss bit, right? So we can talk about this maybe in this one. So content addressable memory, which is abbreviated with CAM, as following things. One, as looking at the hierarchical, you are going to have the read signal when you want to read. You are going to have write signal when you want to write, but and at a given address. So you can read write at a given address, but here one more extra thing other than SRAM and DRAM, you are going to match the specified key, right? Which is actually like most of the time it's given on kept on bit lines. So on bit line, I'm going to keep the required key and it's going to be matched with the available address or available data at the cell, and it's going to tell whether it's matching or not. If it is matched, it's 1. If it's not matching, it's equal to 0. Note that like the case of SRAM, DRAM, you are going to have like column decoder and row decoder and lots of cells were there, right? So this is for row and this is for column. You had lots of cells over here. Similar to that, this is not only one cell, but you are going to have many cells like this here. One cell is here and many cells. The way you are making 8 cross 8 memory as your project. So you might have n cross n or n cross m number of cells, and that's why each row is going to have the matching address because row has the address. So you can match with the row address. So you can see here it's not only one, there are multiple match you can see on a given given row. Hierarchically how it looks, we are going to talk in the next few slides, but before that let's go one by one. So this was the first thing. The second thing is, if you go a little bit inside, CAM is actually designed with the same SRAM array, which you have studied and which you know that how to design it. When I'm saying how to design it means it's all about how to find out the W and L of a given transistor. So you know how to do that with the access transistors and the driver transistors of these two NOT gates. So this is bit and bit bar, and this is word. And by the way, this particular bit is you're going to call it a Q, and this you're going to call it a Q bar, right? So definitely this SRAM is going to use to store the physical address, which is part of this SRAM array, and you're going to add some more logic, other things with this with respect to the transistor, so that you can have the match thing. Definitely the other line is going to be equal to clock. Note that the whole thing is working uh, with the uh, with the clock signal, and as I kept it as a uh, title of this slide, it's a very much useful for the translation look-aside buffer. So if you're studying microprocessor or microcontroller, you might be knowing that there is something called TLB. TLB is the one which is matching the role of TLB is to match the virtual address with the physical address. If it does not match, then look, microprocessor has to search for the whole lookup table with the all the data available at all the addresses going from all 000 to all FFF. So it takes lots of time. So if we have something which is available in the virtual memory of CAM or the virtual address of the CAM, and its matches with the physical address, it will be very fast, and this will be acting as a cache memory for a microprocessor, right? So in that way, the most uh, important application of such a CAM is for the TLB or the translation look-aside buffer, right? Where, as the name is buffer, it's keeps the data for small time, and then on every clock, it's on the requirement, it's going to change it. So it's a TLB, which is used for the microprocessor or the microcontroller, right? So on the clock, if match data are equal to 1, this is what we want, that all the match data, as this is multiple lines, so it's a bus of different lines. So in that case, all of them are 1, then this is acting as 0 and miss equal to 0. When clock equal to 0, as we are making maybe with respect to clock, when clock equal to 0, if you want to read the data at clock equal to 1, simply you can remove this one and have the logic 1, right? And accordingly you can work upon it, and you can see that if all the matches are 1, means matching the virtual address with the physical address, things are fine. Then miss equal to 0, so there is no mismatch, and yeah, you can say that it's match also, right? So both are generally complementary with the propagation delay of this AND gate, right? So that is how generally these TLBs are designed. Let's go inside this, how these TLB look like. So now, as I told you, if we are looking at the CAM cell, which has the standard SRAM, I believe you remember how to read and write the SRAM. If you forgot, I suggest that you go with the lecture given on like maybe previous 2-3 lectures back. If you go, you know how to read and write in the cell, okay, in the SRAM cell. Now, here what is happening? Let's assume that you want to check whether it's matching or not. So here, few more transistors has been added, which is acting as a CAM. So here, this is extra CAM. By the way, the whole thing is known as CAM. I'm just keeping it aside CAM just to make sure that this is a new part other than SRAM, right? And here, whatever the Q or cell is available, I'm feeding over here to the transistor of this one, and other side is going to be fed to the transistor of this one. Now, as if you remember, just few slides back, I told the virtual address or the address or the data or the key which I want to match with, it has to be kept on bit line. So let's assume that I kept what I require on bit and bit bar, right? I kept this on bit and bit bar. So I have kept the virtual address over here, or the virtual, I would say that address is already by word. So virtual data which I wanted, I kept it on bit and bit bar. Notably, that will be complementary to each other. And note that we are in the phase when we want to evaluate. There are 2 phases of the evaluation. One is pre-charge and one is evaluation. During the pre-charge, bit bar may be 1, and match is also 1. Note that match is also precharged to 1. So this is also precharged to VDD, right? And next stage, when I'm going to read the data, at that time, look, these two values, I can take maybe better color so that, so these two values are already filled, or there is some data is available. At that time, if bit is equal to 1 and bit bar equal to 0, note that when bit equal to 1, which is connected over here, that will make this transistor in on mode and other transistor in off mode, right? Because of 0, it's off mode. So because of this off nature of this transistor, look, this particular line will not go anywhere. It will be remain at VDD or previously charged. Now look at the other side, what is happening. When this is on, at that time, if address over here is 1 and 0, then you are in the safer side. What I mean to say, if this is 0, look at this, you have to follow the yellow line. This 0 is going here and make this and because of that, this line does not change from VDD. It remains at VDD, and that is what we wanted. Look, if it goes to 0, means it does not match. You look at here, this one and this one are matching, and this 0 and this 0 are matching. That's why I think these things are happening. If it is reverse, let's take another example where it might not match, okay, or maybe certain possibilities where some different outputs will be there. So now let's assume that the data is available over here as 0 and 1. So this is 0 and this is 1, right? No problem. In that case, because of this one, this particular transistor is on and this transistor other side is off, right? Now we have to see what is available at bit and bit bar. If bit is equal to 1 and bit bar equal to 0, what is going to happen? Because it's a different values than which we wanted. So in that case, this 1 is going to make the connection and this is on, and because of this one, it does not make the connection. So if you are looking at only at this side, which is not connected to 0, this remains at VDD. However, because of this connection, or you can say that after the propagation delay, which is required from this transistor and this transistor, this line is going to go from VDD to 0 volt because there is a strong connection from this point to this point, right? There is a strong connection from this point to this point. So this line is going to go from VDD to ground. If it is going VDD to ground, what is going to happen at the little bit top level? Match is becoming 0 instead of VDD, and miss equal to 1 means you're going to say that okay, it's not matching with what you wanted as a virtual address with respect to the physical address. Physical address, note that it was stored in this cell. The cell, which is SRAM, we are going to call about this cross NOT gates only, right? So that you can have the things. So if there is a mismatch between these two, match equal to 0. If both are matching, match is not equal to 0 and it remains at the precharge value where we have made it at like VDD. If you want, like we can take one more example just for the completeness, right? So let's assume that bit equal to 0, bit bar equal to 1. Because of bit 0, this is going to be off. Because of bit, this is going to be on. So this is on. Now what data is here? So as I told you, bit is 0, then this should be 0 and this should be 1 to match the data. So if this is 0, then look, this is off, upside is off, and because of this one as 1, this transistor is on. So in this case, this match line is not making the connection with 0 at all, right? So what will happen? It will latch the previous value, right? It does not discharge. So this line does not discharge, and you are going to have the previously latch value, and that value was VDD. So VDD will remain same, and in that case, you can say that yes, it's matching the cell. Accordingly, you can have more number of cell in maybe horizontal direction, vertical direction. Accordingly, for a given address, you can find out whether it's matching that or not, right? So this is one part. Now, how does it look like if we are talking about 4 CAM memory, CAM array? So each one of the block, this green block is a cell, right? Each horizontal line, which is coming from the row decoder, which is of blue color, all are word lines, which is of this one, right? Word line will tell you that which address has to be checked or it has to be matched, right? Same as we are doing for the case of SRAM or the DRAM, right? And from the column circuitry, look at this. This data is bidirectional, and here there is a bit line. This is bit bar. So this might be bit 0, and this is bit 0 bar. This is bit 1, and this is bit 1 bar, and so on, right? Each bit lines are same bit, which is shown over here, and these are the places where you are going to keep the virtual address which you want and which you want to match it. So that's why this is not the unidirectional, this is a bidirectional bus where data can be written, data can be read, or anything can be done. But in the case of read and write, it's not that way. It's just a unidirectional, right? Okay, and you can see over here, extra things are match lines. So match lines are also given horizontally like word line, but it will have 4 extra transistors. Note that by looking at this particular CAM cell, you can find out how many number of transistors are required. So here, if in the case of SRAM, required 60 transistors, so that's why it's known as a 60 SRAM. In this case, it requires 10 transistors. That's why it's known as 10 TCAM, because 4 extra transistors, just to make sure that match is going from VDD to ground or not, or with the matching with the virtual address and the physical address, we are doing it. So there are 10 transistors. That's why it's a 10T cell. And of course, this requires, other than this also, we have many things like the match lines has to be precharged to VDD. In that case, we are using, look, wherever we require to precharge, we are going to use the simple thing which is called pseudo NMOS gate, right? You know what is pseudo NMOS gate is, where we are keeping the load of PMOS with gate connected to ground. And in another case, I am also keeping another logic which is of clock. And if you look at all these things separately, you can see that having this one as top, and here there are many matches are in parallel. So there is one transistor here, but other matches are in parallel. So such kind of structure makes the memory or the structure as NOR, right? Because all NMOS having the structure in parallel, so at the MIS structure, you are going to have the NOR logic, right? or other way around, you can use NAND or whatever is given at the beginning. You can use this. In this particular thing, it's non-logic with the clock, right? So this is what about TCAM. But if you look at the refined TLB path, in that case, it's not only about CAM and SRAM. In reality, you have to incorporate clock also. And we have to make sure that it's all about, like, when you are doing it for microprocessor or microcontroller, the most important part when you are dealing with the data, it has to be sync with each other. The people are calling this one as a handshaking signal. When one is happening, other event has to happen, or that way, like, people are making asynchronous also. But if you are making the synchronous design, then I'm saying that the match line has to be available before the strobe is available. If I don't keep this dead match, and it might happen that this cam is working at clock and match is coming little bit with delay, and you might not have enough availability of propagation delay of AND gate, so that word line coming on sync with the required delay. So in that case, what you can do, you can use the delay are nothing but even number of inverters. The way we are designing, you are now expert of designing inverters. So back to back inverters, where each one of them maximum TPHL or maximum of TPHL or TLH will be taken as delay of one inverter, and adding so many inverters in cascade is going to determine the delay. So after delay, you're going to have the strobe signal. So you can see here, after delay, you are sorry, and to make sure that in between these two, match line is available with the decision either 1 or 0, right? So once that decision is available and this is also available, after this there has to be the propagation delay from this AND gate, which is going to give you the word line, and accordingly you can design it with everything as per the requirement of your timing requirements. So that is what kept here. And if you want to understand more things in detail, maybe you need to understand what is the microprocessor architecture, right? And how these TLBs are kept as a part of that one, right? So right now we are not going into that, and even we are not going into the memory IO mapping. Otherwise, if you are going to do that, then you understand that how these timing, that's all the timing things are important to each other, right? So this was one thing. Now let's look at the one more cell, which is again a TCAM, but the only difference in this TCAM cell is we are adding two more lines, search and search bar. Note that this search and search bar are similar to what we were doing with the bit and bit bar earlier. So in earlier case, you are keeping that you are keeping the data on bit and bit bar, right, to match the data. Note that right now the structure is same, but because of the differential structure, you can share these two transistors so that the number of required transistors become lesser, right? So other than that, I'm adding extra search and search bar, where I'm going to keep the key. Keys are here. Whatever the key are required, key and key bar will be here. Where bit and bit bar are the regular one, which is happening, or these two are the regular SRAMs, right? Now, what we are doing, let's understand one thing, that there are two signals which are easily visible from here, which are A and, I'm calling it A and B. So in A and B, there are four possibilities are there. Both are 0. One of them is 1, and both are 1. Now, right now, for a time being, do not read this one. Still, we are talking about CAM. Extra T is added, whose name is ternary. Okay. Earlier, it was just a CAM cell, but now we are making the TCAM cell where it's a ternary. You are okay. So TCAM cell is that which is ternary, where there will be three different data: logic 0, logic 1, and don't care. But for time being, do not look at this. We'll look at that maybe later. So if A equal to 0 and B equal to 1, what is going to happen? If A equal to 0, definitely this is going to be 1. And B equal to 1, this is definitely equal to 0. If A equal to 0, note that this particular transistor is going to be off. This is off. And other transistor is going to be on. Now the whole thing is depending on what you want to search. So search wise, if this is 0 or 1, which is, look, note that one more important thing before going to this. If this is 1, this has to be 1. And if this is 0, this has to be 0, right? Because there is a switch and it has been designed such a way that this is 1, right? So if search is equal to, let's assume that equal to 0 and this is 1. If this is 1, unfortunately, this line goes to 0, right? So it cannot search 1. But if you keep other way around, in this case, if search equal to 1 and this equal to 0, what is going to happen? This will become such a way that none of the transistor will make the connection to 0 and it will match. So I can say that if 0, 1 is there, it's matching with the condition for 1. Note that when I'm saying that it's related to search equal to 1. Now, let's assume that search equal to, okay, now let's assume the another condition when A equal to 1 and B equal to 0. If A equal to 1 and B equal to 0, definitely other side is 0. And because of the switch at the settled value, this is going to, and this is going to be, this is equal to 1. This is going to be 0 and this is going to be 1, right? And this is going to be 0 and this is going to be 1, right? Because of this A equal to 1, it will make connection of this transistor on. Because of B equal to 0, it will make this connection as off. And now let's see what is going to happen, or what value of search is going to match the value. So if search equal to 1 right now and search bar to 0, note that search equal to 1 will make this transistor on and it will create a mismatch, right? It will create a mismatch. It's not creating a match, but it's creating a mismatch. So in that case, if this is equal to 0 and this is equal to 1, so in that case, this transistor is going to be off and other transistor is going to be on. So in that case, this particular match line does not go to 0. So in that case, we can say that it matches the value of 0. So it search for 0 and gives the value for the combination of 1 and 0 of this one. But what is going to happen if A and B both are 0? If A and B both are 0, then what is going to happen? Look, other side is going to be equal to 1. Other side, again, this is 1. So bit 0 is also 1 and bit 1 is also 1. Now, both are 0. So in that case, what is going to happen? Both the transistors are off. Now, no matter what value of search you are going to give, means search as 1 or 0 or search bar as 0 or 1, it is not going to change the value of match. So this is matching the value of both 1 and 0. Now look at this such situation. You can say that it's a don't care what value of search you are giving. It does not matter as long as A and B are stored with 0 0 value. The match is 1, right? So it's not only searching the value 1 and 0, but if you want to search the value of don't care, you can find out that. So there are 3 values. Now look at the other thing, which is 1 1. When this is 1, this is 1. So this is 0, this is 0. And because of this 1 1, both the transistors are on. So now, unfortunately, search and search bar are actually complementary to each other. So it will make one of the transistor on and match goes to 0. In this case, are matching for the mismatch. Any value of search is going to give you mismatch only, right? So what I'm going to do, I'm not going to implement this value ever, or I'll make sure that 1 1 is not going to happen ever, right? So if it is happening, then look, no matter what value of search and search bar I am giving, the output is only an on mismatch, not match. But I'm looking for match. So match are possible in first 3, which are AB are 0 0, AB 0 1 or 1 0. So in 0 1, it matches the search of 1. In the case of 1 and 0, it matches the search of 0. And in the case of 0 0, it searches the case of match either of the case. So it's don't care, it's going to match in any of the case. If A and B are 0, it's going to match any value. So it has 3 combination of matching, which is 1 0 and don't care. This is very much important for a case when you are in communication networks, where you have to send the data at a particular continent rather than the subnet mask. In that case, you can use such kind of ternary data where you don't care about the subnet address. So in that case, it's very popular to use the TCAM, and such architecture is used. And at the hierarchically, of course, you can't avoid to have such kind of structure. You need to have 4 cross 4 TCAM array, which is also made with the same fact which we have done over here. Where is it? Okay. Yeah. So this is all about TCAM, which is dealing with 3 data, 0 1 and ternary